Assalamualaikum warahmatullahi wabarakatuh. I'm Imanina, one of the member of Group 7, and we present to you a topic of synchronous motors. Let us begin with definition and characteristics. What is synchronous motor? A synchronous motor is a AC motor. An AC motor is a motor that takes AC supply as an input and converts it to rotational motion. An AC motor speed depends on the supply frequency, whereas the DC motor speed is controlled by the voltage. A synchronous motor refers to an AC motor that runs at synchronous speed. At the steady state, the rotation of the shaft is synchronized with the frequency, and the rotation period is exactly equal to an integral number of AC cycles. It consists of two parts. One is stator and the other one is rotor. These motors contain multi-phase AC electromagnets on the stator, creating a magnetic field, and it rotates in time with the oscillation of the line current. And these all the keywords to remember the definition of synchronous motors. Let's move to characteristics of synchronous motor. Number 1, speed. Speed of the synchronous motor is range between 150 rpm to 1800 rpm. The speed is synchronous and does not depend on load condition at all. Speed always remains constant from no load to full load, and the relation between the pole speed and frequency is defined as N equal to 120 times F divided by P, where N is speed of motor in RPM, F is frequency, and P is number of poles. Number 2, maintenance. The synchronous motors use brushless exciter, which decrease the maintenance problem. A brushless exciter is a small direct coupled AC generator with its field circuit on the stator, and the armature circuit is on the rotor. The three-phase output of the AC exciter is rectified with the help of solid-state rectifier. Next, number 3, efficiency. The synchronous motors are highly efficient, and it is much greater than induction motors. Next, rating. The power rating of synchronous motor range between 150 kilowatt to 15 megawatt. Number 5, starting torque. External force is required to start the synchronous motor as it has no starting torque. And lastly, number 6, power factor correction. The synchronous motor is capable of being operated under a wide range of power factors, both lagging and leading. So, these motors have high power factor correction. Hence, they are used in areas where power factor correction is really needed. So, power factor correction is a technique which use capacitor to reduce the reactive power component of an AC circuit in order to improve their efficiency and reduce the current.
Hi, I'm Elis Farhana Shukya binti Azmi with the metric number of 2015654. I will now continue with the working principle of the synchronous motor operation. So, the synchronous motor depends on two components interaction, which is the stator and also the rotor, whereby the stator is the stationary part and the rotor is the rotating part. So the rotor is supplied with DC supply, meanwhile the stator has 3 phases of AC power supply and also 3 phase windings. Therefore, this stator winding creates a 3-phase rotating magnetic field. So now I will first begin with the first part of its principle of operation, which is excitation. So what is excitation? Well, excitation is the process of producing magnetic flux by passing current in the field winding. And this synchronous motor is doubly excited, whereby both the stator and the rotor are excited separately. So the first one is, when the 3-phase AC supply is given to the stator, it produces a rotating magnetic field, which is called RMF, with a synchronous speed. And the second one is a DC source, that it is used to excite the field winding, which magnetizes on the rotor to generate a constant magnetic field and also stationary rotor poles that interacts with the stator RMF. As we know before, the stator winding creates a 3-phase rotating magnetic field. So what is a rotating magnetic field? Rotating magnetic field is the magnetic field that has moving polarities, and that polarities are vary according to the time. So due to this variation of the poles, it will induce magnetic fields, and it is actually induced due to 2 reasons. The first one is due to the 3-phase windings of the inner stator, which are equally displaced 120 degrees apart. And the second one is because the supply is equally distributing the current in all those 3 phases, resulting in the same magnitude of current. Next, this rotating magnetic field is actually depends on the frequency of the supply and also its number of poles of the motor, whereby that number of poles should be constant. Here we can see that its synchronous speed is given by the formula of Ns equals to 120F over P. So next, for the DC supply, the poles are fixed on its polarity. So when the rotor and the stator have the same pole on the same side, it will repel each other and only attract when they have opposite poles, which will then create positive half cycle and also negative half cycle respectively. And by then, the rotor supposedly tilted or pulsated at one place, either it is in anti-clockwise direction or in clockwise direction, but it will not do a complete rotation.
Assalamualaikum warahmatullahi wabarakatuh. My name is Sofia Atira binti Muhammad Sharifuddin with metric number 2018826, and I will present why the synchronous motor is not self-starting. So, the main reason why this synchronous motor is not self-starting is because the net torque experienced by the motor is equal to 0. Why? Because in this synchronous motor, we already learned that a 3-phase AC supply is given to the stator, producing a rotating magnetic field which is called RMF in the A gap, but the rotor has its own magnetic poles which are already fixed, produced by a DC current flowing to the rotor windings. But in order for this synchronous motor to be self-starting, the rotors and the stator's pole has to be magnetically locked with each other. For example, as shown in the figure, the source of the stators has to be attached with the nose of the rotors. However, we can see that in this synchronous motor, when the motor is operating, the stator will rotate in a very high speed of RMF in a clockwise direction, leaving the rotor behind because initially the rotor is stationary. In this figure, we can see that when the synchronous motor is start to operate, if the same pole of the stator and rotor are facing each other, they will repel and generating an anti-clockwise torque on the rotor. But if the opposite pole is facing each other, they will attract and generating a clockwise torque in the rotor. So the rotor will end up vibrating in between source and nose of the stator. This is due to the certain inertia experienced by the rotor, and the speed of the stator RMF is too fast for the rotor to catch up. As you can see, before the nose of rotor could magnetically lock with the source of the stator field has shifted its position, so when the nose of stator comes in the area of the nose of rotor, they will repel each other. Hence, we can say that the motor will start itself unless the rotor is brought up to the same speed of the RMF of the stator. This is because the torque reverses in a single RMF cycle since it experiences attraction and repulsion at the same time. So, the net torque is equal to 0. Next, in this slide, I will explain how to make this synchronous motor self-starting. The first way is to insert the external prime mover to the motor. This prime mover will rotate the rotor at the speed of RMF of the stator. When the rotor starts to rotate at the speed of RMF, we will remove the prime mover and give DC supply to the rotor. This DC supply will induces the nose and source pole of the rotor, and because of the prime mover, the motor start to rotate with the same speed of RMF, causing the opposite pole of the rotor and stator to face each other and get magnetically locked. Then, the synchronous motor start to working as a self-starting motor. The second way is to provide a special winding to the rotor poles, which is known as a damper winding. This damper winding will actually carry out the same task of the induction motor in the rotor windings. Therefore, due to this damper winding, a synchronous motor will start as an induction motor and continue to accelerate. The exciter for this synchronous motor moves along with rotor. When the motor attains about 95% of the synchronous speed, the rotor windings is connected to exciter terminus, and the rotor is magnetically locked by the rotating magnetic field of the stator, and it runs as the self-starting synchronous motor.
Assalamualaikum. I am Dayang Nur Hafizah binti Awang Daramat. My metric number is 2013230. I am going to continue with the equivalent circuit of synchronous motor. A synchronous motor is a doubly excited system where it is connected to two electrical systems. First, a three-phase supply is connected to the armature winding, and then a DC supply is connected to the rotor field winding. We can see from here that we have an equivalent circuit for one phase for a three-phase synchronous motor. From the left side, we have V, which is the terminal voltage per phase applied to the motor. And in the circuit, we can see that we have a current flowing, which is IA, which is also known as the armature current per phase drawn by the motor from the supply. And then we have the impedances. The first one we have RA, which is the effective armature resistance per phase. And then we have XS, which is the synchronous reactance per phase of the motor armature winding. And then at the rightmost side, we have the EF, which is the excitation voltage. Okay, next we proceed to the calculation part. Okay, the first step is to calculate the synchronous impedance, where it is the sum of all impedances in the circuit. Here we have the first equation is ZS equals to RA plus JXS. Then the next step is to apply KVL to the circuit. From the left side, we have V is equals to ZS times IA plus EF, where that is how we get the second equation, V is equals to EF plus IA ZS. From the first and the second equation, we get the third equation, where we substitute the value of ZS from the second equation with the first equation, and that is how we get V equals to EF plus IA multiplied by RA plus JXS. Then, when we rearrange the equation, we will get the fourth equation, which is EF equals to V minus IARA minus JIAXS. In the fourth equation, we need to note that we have now IARA and also JIAXS, where IARA is the voltage drop per phase in the armature resistance, and then IAXS is the reactive voltage drop per phase due to the armature resistance and armature reaction effect. Next is to find the armature current. The armature current, we can find it by rearranging the equation 4, where we have IA is equals to V minus EF over ZS. From here, we can also get the ER, which is the resultant voltage in the armature current, where ER is V minus EF. Lastly, we need to know that the ER and also V plays important role in the equivalent circuit, as it helps us to understand the operation of the motor. So there are three cases. The first case is when ER is equals to V. We can say that the synchronous motor is normally excited. Next, when we have ER is lesser than V, the synchronous motor is said to be under-excited. And lastly, when we have ER is larger than V, the synchronous motor is said to be over-excited.
Assalamualaikum. My name is Nur Kisna Zulaika with metric number 2015534. Now, I will explain about the differences between synchronous motors and induction motors. So this will include about the constructional part, starting part, power factors, types of machines, and also applications part. So there are basically many more differences that you can get where you are doing some more detailed research on it. Firstly, for the constructional, as we can see here, there are two images of how to construct the induction motors and the synchronous motors. What are the differences? For the induction motors, it uses a salient pole rotor, which rotor winding is mounted. Rotor winding is fed with a DC supply, hence it needs of the slip rings. So how to create a slip? Slip is created basically by the differences between the rotating speed of the shaft and also the speed of motor's magnetic field. This also allows for increase of the torque. Meanwhile, for the synchronous motors, it uses a squirrel cage rotor or a one rotor. In one rotor, the windings are permanently short-circuited, hence no slips are required. This is also because the rotor and the stator are in sync. Hence, the AC supply are required. Okay, next, for the starting part, for synchronous, it is not self-starting, while for the induction motors, it is a self-starting torque. Why the synchronous it is not self-starting? It because it requires additional a starting mechanism to initially rotate the rotor near to a synchronous speed. Meanwhile, for the power factor, for the synchronous, it has both power factor of leading and lagging, while for the induction motors, it has only lagging power factor. So, for the last part is for types of machines and also application parts. So, for types of machine, which is for synchronous, it is a doubly excitation machine. What it means by that? It means by its armature winding is connected to an AC source while its field winding is excited from a DC source. So, for the induction motors, it is a singly excited machine, which is means by its stator winding is energized from an AC source. So, for the last part, which is for the application, for synchronous, it is used for driving mechanical loads at constant speed and also for the power factor correction for electrical. Meanwhile, for the induction motors, it is used for driving mechanical loads only. So that's all from me. Thank you.